All right, we're going to have a look at a question from the 2018 Northern Hemisphere exam. So, nitrosyl chloride is a highly toxic gas used in the chemical industry as an oxidizing agent. The formation for the reaction of nitrosyl oxide from nitrogen monoxide, otherwise known as nitric oxide, and chlorine. So, this forms at above 100 degrees. So, one thing we might want to note down here, whether it's important for this question or not, is because delta H is greater than 0, this is an endothermic reaction. Always something good to note down. So we're told that it happens above 100 degrees, and we can see that this is happening at 150 degrees, so the reaction will occur. Something else to note is that the reaction is occurring in a 4-litre container. So the first question is stock as, really straightforward. Experiment 1 happened with 2 moles of nitrosyl chloride. The next one happens with 4 moles of nitrosyl chloride. So both into a 4-litre container. So we're asked to find out which is going to have the highest rate for the reduction of chlorine. So we maybe just draw a little picture might help us out. So here's experiment 1, and here's experiment 2. So draw the boxes the same size because they're both supposed to be representative of 4-litre containers. If we draw particles to represent our reagent gas, in this one here, because we've got twice as many moles of gas, we have twice as many particles. And one of our key ideas is more particles gives us more collisions. So that's one of our big picture ideas. So experiment 2, which one is going to have the highest initial rate? Well, experiment 2 will have the highest rate, so choosing that gets us 1 mark. But what we need to say is, as there is a higher concentration, we hope I spelled the word there correctly, the context, higher concentration of NOCl. In experiment 2, there will be more, now keyword, successful. Therefore, a higher initial rate. Again, spelling's init PO rate. Right, so that one's pretty easy, 2 marks. The next question is a little trickier. So for experiment 1, the concentrations of NOCl and NO were equal at equilibrium. All right, and this is actually, noticing this word here really helps us unlock. Then what conclusion can be made about the relative concentrations of these two in experiment 2? For a lot of students, this was just a guess. So there's something we can do with this, which is not immediately obvious. We can get in and we can draw an equilibrium graph of the initial situation. So let's think about experiment 1. Let's think about experiment number 1. Experiment 1. And we're going to draw ourselves a time versus concentration graph. Yep. So time's down here, concentration is over here. So let's think about what's injected in. I'm just going to change colors for a moment. All right, so we've got this nitrosyl chloride, this strange chemical we've never heard about before. But we can go through and we can work out the initial concentration because we're told that there are 2 moles in there and it's in a 4-litre vessel. So therefore, that equals 0.5 molar. moles per litre, however you want to say it. So on this graph straight away we can mark down this 0.5, and this is the initial concentration of the NaCl. Now if we're thinking about the NO, well, the NO, it goes into an empty vessel, so it starts out at 0. And then we're told that they're equal. When we look also at the mole ratio of NaCl to NO, 2 to 2, which is equivalent to 1 to 1. So this means that as the concentration of NaCl is getting smaller, the concentration of the NO2 must be getting higher at the same point, and that they must meet in the middle. Okay, and this point where they're going to meet is going to be 0.25. Obviously this concentration here is in mole strength. Yep. Alright, so that's where they meet when the system reaches equilibrium. When we go back and look at the equation and look at the mole ratio of the Cl, the Cl is half as much as the NO. So when we think about that mole ratio of Cl to the NO, that mole ratio is 2 to 1. So when we're going to draw in the chlorine, it's going to get to half. I'll make it about half. Try and show it coming to equilibrium at the same point. So here's our cast of characters. Here's our Cl2. In blue, we've got our... my bad. There's our NO in blue. And then the green line represents the NaCl. So we can actually go through and work out their equilibrium concentrations. So we can actually go through and work out, and we can say here that for experiment 1, or at experiment 1, actually let's try the black again. Experiment 1 at equilibrium. The equilibrium expression, well, we'll have NaCl on top, raised to the power of 2, and then we'll have our NO on the bottom, again raised to the power of 2, and our Cl2 there. Sub in our values. Let's sub in our values. So we've got 0.25 squared over 0.25 squared times by 0.125. Now, what we can do here, we can get a bit jiggy with our mathematics. These are equivalent, so they cancel each other out. Yep. And then we end up with essentially 1 divided by 0.25, which gives us 8m to the power of -1. And you might go, oh, but that hasn't answered the question. That has not answered the question. We need to then compare to what would happen in experiment 2. So let's try and do the same thing for experiment 2. The shapes of the graphs are going to be exactly the same, but our initial concentration of NaCl is going to be twice as much. So it's going to be 4 over 4, which is going to be 1 capital N. So it's going to start at 1, and it's going to come down, and it must meet in the middle again if the concentrations were equal. And so that would meet in the middle. So, and then again, the chlorine would be half as much again. So if we go and work out the values for these, this would be 0.5, and this would be 0.25. Capital M, capital M. We can drop those very quickly into the same equilibrium expression. And so we're going to end up with 0.5 squared times by, and then on the bottom 0.5 squared times by 0.25. 0.25. Again, by the power of mathematics, cross out, and we end up with an answer which is 4 m to the negative 1. Now you might go, key insight, 8 does not equal 4. And the only thing that can change an equilibrium constant is a change in temperature. The conditions are the same. So what needs to happen? This actually needs, this top value needs to get higher. This top value needs to get higher, and this bottom one needs to get lower. How is this top value going to get higher? Well, we're going to need to favor the forward reaction. So what we'll see is at experiment 2, the NaCl, or the concentration of NaCl, we need to be higher than the concentration of NO, so that the equilibrium constant can equal 8. Alright. That's one potential way of looking at it. There's another way of looking at it, which is the examiner's report. If you like it, like it.